Hello everyone, this is a recorded version of a talk I gave at the 32nd November Tango on the history and philosophy of mathematics and entitled Sturm's theorems in projective geometry and their circulation at the beginning of the 19th century. My thesis work consists of a biographical study of the 19th century mathematician Charles-François Sturm from Geneva, whose portrait you see here on the left, next to his friend the physicist Jean-Daniel Colladon. Sturm was originally from Switzerland but later became French. Here is a very short biography of Sturm for the period we are going to see, from 1803 to 1813. His friendship with Colladon began when he was at the Collège de Genève. And it was also at the Collège de Genève that Sturm had his first lessons in mathematics, which had recently been introduced into the curriculum, and mainly arithmetic. Then Sturm studied at the Académie de Genève, at the Auditorium of Belles-Lettres, and later at the Auditorium of Philosophy, where he was taught mathematics at a higher level, algebra and geometry. In January 1823, he published his first article in the French journal Les Annales de mathématiques pures et appliquées, also called the Annales de Gergonne. An important element to know is that during his studies at the Geneva Academy, at the Auditorium of Philosophy, Sturm had two mathematics teachers, Jean-Jacques Schob and Simon Rouillier, who is best known as the author of several mathematics textbooks, including polygonometry, which deals with polygons as its name suggests. In 1823, Sturm became the tutor of Alphonse de Roca in the de Broglie family. Alphonse was the orphan son of Germaine de Stael, a famous French author, and Albert de Roca. His sister Albertine was married to Victor de Broglie, an important actor in the future monarchy, La Monarchie de Juillet. Here is the rest of the biography. Sturm is mainly known for his theorems on the number of real roots of an algebraic equation in 1829, but before that, he was the author of several theorems in geometry that we will see today, theorems that germinated in his mind during his first stay in Paris in 1824. These theorems were published in two parts in the Annales de Gergonne in 1826. This is the plan I intend to follow for this presentation. First, I will introduce the geometric context in which Sturm's theorems will appear. Then I will give some details of Sturm's publications presenting these theorems. And finally, I will talk a little about the mathematical circulation of Sturm's theorems. Now let's focus our attention on the geometric context. Sturm's work in projective geometry, carried out between 1824 and 1826, took place in a context of scientific publications, characterized by the publication of numerous books and memoirs written by important actors in projective geometry. From left to right, we have, for example, Lazare Carnot, Gabriel Lamé, and Jean-Victor Poncelet. In 1806, Lazare Carnot published an essay sur la théorie des transversales, in which incidence properties play a fundamental role in geometry. In 1817, Gabriel Lamé presented his methods of indeterminate multipliers. Charles-Julien Briançon wrote a mémoire sur les lignes du second ordre, in which the notions of poles and polars are placed at the heart of his theory of conic sections. And in 1822, Jean-Victor Poncelet published the famous Traité des propriétés projectives des figures. And we are witnessing a modification of the practice of geometry. The practice of geometry was transformed from a geometry of problems to the development of geometric theories. When he arrived in Paris at the end of 1823, Sturm met several mathematicians, including Servois and Poncelet. He updated his knowledge of geometry and he wrote a letter to Colladon, preserved in the Bibliothèque de Genève, giving him some news and some details. In this letter, Sturm wrote, "I have to tell you about a project I have found. When I arrived in Paris, I began to read Monsieur Poncelet's beautiful work on the projective properties of figures. This book deals only with lines and surfaces of the second degree. The author, with whom, incidentally, I am about to become acquainted, not wishing to borrow anything from algebraic analysis, has introduced a certain continuity principle, and combining it with projective considerations, he has arrived by these equivocal methods at beautiful results, already known to a great extent. But he did not feel that almost all the propositions he established are basically dependent on each other. By thinking about them at length, I found that they can be linked to a common link and make up a fairly complete body of doctrine. I encountered several new and difficult theorems on my way. So this is an illustration of the continuity principle of Poncelet. Let be a circle, let S be a point inside the circle, and let be the lines A, B, and CD. It is quite easy to show that the equality written here is true by using properties about angles and arcs of a circle. And by virtue of continuity principle, we are allowed to conclude that the equality remains true even if the point S is outside the circle, which would be difficult to prove without this principle. The continuity principle will be discussed in the mathematical community, and according to Cauchy in a rapport à l'Académie royale des sciences, the continuity principle is only a very strong addiction. Another point of discussion among mathematicians about projective geometry concerns duality. In 1827, there was a controversy between Gergonne and Poncelet over the authorship of the concept of duality. Duality is an important tool in projective geometry, and to illustrate it, I take the example of Blaise Pascal's hexagram theorem. Let us consider a conic, here an ellipse. We consider 6 points on this conic, and we connect some of them as shown in the figure. Then the points of intersection P, Q, and R are aligned. The duality consists in this. We obtain a new theorem by changing some terms of the first theorem, and for example, by changing the 3 points aligned by 3 concurrent lines, this gives us Briancham's theorems. We can say that Briancham's theorem is the dual version of Pascal's theorem. Further on this letter to Colladon, Sturm wrote, "The fundamental proposition of the first part of my dissertation consists in a certain relation which takes place between the 6 points of a section determined on an arbitrary straight line, which intersects 3 conics having 4 common points. This is the main proposition of Sturm's theorem. There is an analogous relation which I also discovered between the sections of the 3 pairs of tangents which can be led from the same point to 3 conic which have 4 common tangents. This is the dual version. From this derived without calculation the theory of poles and polars, the harmonic division, all the geometry of the roots, Pascal's hexagon, etc. Now let's look at Sturm's theorems and their history. In March 1824, Bobillier, his math teachers at the Geneva Academy, publishes a theorem to be proved in the Bibliothèque universelle. In February 1825, this is a publication of an article on regular polygons, which is a response to Boubillier's challenge. Sturm remarks on the continuity principle of Poncelet. In March 1826, this is the publication of the first part of the mémoire sur les lignes du second ordre, in which Sturm redefines the themes of projective geometry from an analytical point of view. In December 1826, this is the publication of the second part of the mémoire sur les lignes du second ordre, in which Sturm published his main theorems on 3 conics with 4 common points and its corollaries. Bobillier published a theorem to be proved in the publication dated 23 May 1824 in the Bibliothèque universelle, and this theorem is this: let there be a regular polygon, and let there be a circle concentric to this polygon, from a point on the circumference of this circle perpendiculars to the sides of the polygon are lowered. The polygon, whose vertices are the feet of the successive perpendiculars, is of constant size, determined by the radius of the circle on the circumference of which the point is situated. And further on, Bobillier wrote, the young man whose task leads him to the cultivation of the sciences, and in particular to the exact sciences, he who aspires to follow with distinction the career that is opening up before him, and to push back its limits, must undoubtedly strengthen the fundamental knowledge that he has received by reading and studying the writings and lessons of the great masters. But he must soon second and replace, at least in part, this passive instruction by a more active instruction which he gives to himself by his own meditations. To develop his genius, he must work with his own strength. He must make himself capable of exploiting the field of science in his turn. And Sturm proved Bobilier's theorem in the Annales de Gergonne after having proved other theorems. And one of these theorems is this. We consider a regular polygon, and to take an example here, we consider the triangle. And let n be a positive integer and L the locus of a point P satisfying the property which is written here. So if n is equal to 1, the locus L is a circle. If n is equal to 2, L is also a circle. But there is a modification when n is equal to 3. L is no longer a circle. Sturm is skeptical about the continuity principle, and by observing this, he concludes that the law of continuity is not observed in all cases. In March 1826, this is a publication of the first part of the Mémoires within the second order, Sturm redefines the terms of projective geometry, but from an analytical point of view. He takes the representation of conics to be an equation of the second degree with two unknowns, x and y. And he studies the special case of three conics with 4 points in common. He is therefore led to consider the cases where solutions of a certain equation are imaginary. And an interpretation work is needed to discuss the constructibility of the points. And Sturm shows that he has appropriated notions such as points at infinity, imaginary points of intersections, ideal lines, or seconds. And he draws consequences that allow him to propose analytical definitions of poles and polars. In December 1826, Sturm states his main theorems. So we have three conics with 4 common points, A, B, C, D, E, and F, and the Sturm theorem states that the 6 points are in involution. Sturm proves a set of theorems, most of them already known, and various propositions that follow from this fundamental theorem. He shows how Descartes' theorems is a special case of these theorems. He brings a new proof of Pascal's hexagram theorem and underlines its originality. He wrote, the demonstration that I have just given of this beautiful theorem, a demonstration that I believe to be new, seems to me to be recommended by its simplicity. In the conclusion of the second part of this dissertation, Sturm draws his plan to prove in a third part a theorem similar to his fundamental theorem. The statement of these theorems will also concern 3 conics, but it will be assumed that the 3 conics have 4 common tangents instead of 4 common points. This third part was never published, but the indication left in the 1824 letter to Colladon suggests that the missing theorem should be the dual version of his fundamental theorems, and this is the dual version of the Sturm theorem. Now let's focus on the circulation of the theorems, and by mathematical circulation, I mean circulation of questions, problems, methods, explanations, teachings, practices, points of view, mathematical theorems or meta-discourses, which take place through oral and epistolary exchanges or in printed forms. Sturm's theorems have been commented on by various mathematicians in the Annales de Gergonne. The first, Michel Charles and Joseph Diez Gergonne and Etienne Bobillier, and Julius Plücker. Plücker and Bobillier are two mathematicians who are interested in the same subject as Sturm and are of the same generation as him. And consequently, Sturm's dissertation occurs in a context of competition where disputes over the priority of discoveries may arise. First of all, there is a generalization of the Sturm's theorem by the mathematician Charles. Charles transformed Sturm's theorems in 1827 to apply it to space geometry and presented it in a more condensed form with its dual version. If three surfaces of the second order are inscribed on the same developable surface of this order, and if by a straight line taken arbitrarily, three pairs of tangent planes are led to them, these planes will intersect any rectilinear transversal at 6 points, which will be in involution. About duality, at the end of the second part of his memoir, Sturm gives several examples of inverse proposition. To take an example, we have the first proposition: when 5 of the vertices of the hexagon belong to a line of the second order, and moreover, the points of intersection of the opposite sides of this hexagon all belong to the same line, its sixth vertex is also on the curve. The dual version of this proposition is the second: when 5 of the sides of a hexagon are tangent to a line of the second order, and moreover, the diagonals joining the opposite vertices of this hexagon intersect at the same point, its sixth side is also tangent to the curve. This is a well-known theorem that only one conic passes through 5 given points. Gergonne had argued for an exposition of duality by means of a two-column representation in an article of the Philosophy of Mathematics sections of his journal. And following Gergonne's recommendations, Bobillier reformulates Sturm's theorems in a very compact way. On the left, we have the main theorems, three conics circumscribed by the same quadrilateral intersect and a straight line at 6 points which form an evolution. And on the right, we have the dual version, the 6 tangents leading from any one point to 3 conics inscribed on the same quadrilateral form abandoned in evolution. About duality, later in 1862, Jean-Victor Poncelet discusses the norm for the presentation of duality. He wrote, "I appreciate as it should be the frankness of this late reflection on the part of a scholar," he is talking about Plücker, "who by proselytism had consented to let his first work be closed with the double colon form, formerly admitted by the partisans of duality, something to which another scholar of the calibre of Mr. Sturm did not consent, at the risk of saying his beautiful studies on polar, reciprocals, etc., truncated in the journal Mathématiques of Montpellier." But according to Poncelet, Sturm was influenced by Bobillier, whom he described as a narrow-minded person with a slow and prickly rigorism. Poncelet, about Bobillier, wrote that he had the great fortune to initiate into geometric and algebraic analysis the naturally upright and mathematical sense of Sturm, a man modest to the point of shyness, whom I have learned to love. But Bobillier had also inspired in our illustrious colleague strong prejudices against the principle, the law of continuity. So as to conclude, I will say that although they did not make a lasting impression on people's minds, Sturm's theorems in projective geometry circulated in journals and mathematical literature and were part of a context of discussions and polemics about the foundations of projective geometry, the legitimacy of its methods, the norms of theorems expositions that the community of geometers should apply. And finally, to remain with the themes of mathematics in times of crisis, I will conclude by saying that the end of the 1820s saw major political changes in France. In 1813, the revolution broke out, which established the new monarchy, la Monarchie de Juillet, and marked the end of the Restoration. To take an example, the mathematician Cauchy had to go into exile in Switzerland because he was a royalist devoted to Charles X. But for Sturm, the new monarchy was good for him because Victor de Broglie joins the new government. He is the Minister of Public Instruction and cults in the first ministry of the reign of Louis Philippe. And in September 1813, Sturm was appointed professor of the mathematics special class at the Collège Rollin in Paris, which is a sign of the liberalism that prevails in the institution. Thank you for your attention, and I will stop here.